Hi everybody, peace be upon us all. We are from Team 11 Chemistry Education 5C. Let me introduce my team. First, AMTA ABDUM MUSTAQIM, SITI AROFATUS SAADAH, and then I am ARYA WIRAYOGA ACHMADA. We would like to present a research journal entitled Using Microwave-Assisted Phosphorylation to Enhance Foaming and Egg White Solubilization by Response Surface Methodology. We hope that you will be able to join our presentation for our discussion session later. The first is abstract. The purpose of this study was to establish optimal condition for microwave-assisted phosphorylation modification of egg white. Response surface methodology was used to model and optimize the degree of phosphorylation, solubilization, foaming ability, and foaming stability of egg white powder. The concentration of sodium triphosphate, microwave power, and microwave time were selected as the main processing condition in the phosphorylation modification of egg white protein. The following three conditions for optimal phosphorylation modification of egg white are the concentration of sodium triphosphate of 33.84 gram per liter, microwave power of 419.38 watt, and microwave time 90 seconds for maximum functional properties, solubilization, foaming ability, and foaming stability, and the concentration of sodium triphosphate of 32.97 gram per liter, microwave power of 429.29 watt, and microwave time of 90 seconds for maximum foaming properties, foaming ability, and foaming stability, respectively. We consequently succeeded in phosphorylation modification with microwave assistance and confirmed the various desirable properties of optimal phosphorylation modification. Introduction. Egg white is a key ingredient in the food industry due to its high nutritional quality. Chevalier et al. 2017 and excellent functional properties. Zio et al. 2016. Stefanovi et al. 2018. Owing to its high foaming properties, egg white is widely used in baking goods, such as meringues, cake, cookies, and chocolate mousses. Lee et al. 2018. Egg white powder has become a popular production as commercial, which is substitute for fresh and liquid eggs. Wang et al. 2018, Lee Chevalier et al. 2017. Because the powder could prevent the microbiological and oxidative degradation, have lower packaging expenditures, and be more convenient to storage and transport. Sponton et al. 2018. It was proven in previous reports that protein modified by phosphorylation had better solubility, foaming ability, calcium absorption, emulsibility, and gelling property than control. Lee et al. 2003-2004, Nayak et al. 2006 studied phosphorylated buffalo milk testing had higher solubility at pH 7.0 and pH 9.0 and so precipitate near their isoelectric points. Egg white protein was phosphorylated with microwave assistance at 500 watt for 2 minutes, and its foaming ability and foaming stability increased by 44.2 and 107.2% respectively, compared with the conventional dry heating method. The microwave technique can significantly shorten reaction times and accelerate phosphorylation process. Lee et al. 2018. Response surface methodology (RSM) is a statistical procedure frequently used to evaluate more experimental conditions for the optimization of various parameters and their interaction with respect to response variables. Zhang et al. 2014. Response surface methodology has successfully been employed in optimizing ultrasonic assisted extraction condition of pyrera isoflavonoid hydrolysis condition for bovine plasma protein and dry head treatment of egg white related to its function properties. Lalancher et al. 2009, Seo et al. 2015, Wong et al. 2017. Therefore, the present study was undertaken to establish the optimal condition for phosphorylation with microwave assistance of egg white protein. The concentration of sodium tripolyphosphate, microwave power, and microwave time. And those conditions were established on the basis of obtaining high solubility %, forming ability %, and forming stability %. The result of this study will provide theoretical and practical reference in food protein of drying process and enhance functional properties. Material and method. Material. Fresh eggs were bought from a local farm. Potassium dihydrogen phosphate, ammonium molybdate, hydroquinone, sodium sulfate, and citric acid monohydrate were provided from Sinopharm Chemical Reagent (CO) Ltd, Shanghai, China. Sodium tripolyphosphate was purchased from Shanghai Aladdin Industrial Co. Ltd, Shanghai, China.
Method 1. Preparation of the egg white protein solution. The egg white protein solution was prepared as previously reported. The 400 ml egg white spirited for egg was stirred for 12 hours at 4 degrees Celsius and then added with 800 ml of ionized water. Finally, the mixing solution was stirred for 6 hours at 4 degrees Celsius and its insoluble protein was removed for the preparation of powder. Method 2. Preparation of the phosphorylated egg white protein powder. Sodium tripolyphosphate was added to the egg white solution to prepare a mixed solution, which was adjusted with citric acid monohydrate pH 2.1 to pH 8.1. The solution were placed into a microwave reaction at certain conditions and then transferred to ice water to avoid further reaction. Finally, the solution were dialyzed to remove pyrophosphate for 1 day against deionized water and dried to the protein powder, in which the outlet temperature and the speed of fluid flow of a spray dryer were 170 degrees Celsius and 1200 ml per hour. The microwave assisted phosphorylation modification was performed by varying the concentration of sodium tripolyphosphate 20, 13, and 40 grams per liter, microwave powder 300, 400, and 500 watt, and microwave time 90, 120, and 150 seconds. Method 3. Response surface methodology. The design expert software, trial version 8.0.6 stat was used to optimize the microwave-assisted phosphorylation modification of egg white protein. Box benchmark was used for evaluating the effect of concentration of sodium tripolyphosphate or X1, microwave power or X2, and microwave time or X3 on the modification of egg white. Phosphorus content, solubility, forming ability, and forming stability were determined as the response variables. The experimental design had 3 replaces at the central point for a total of 15 runs. The runs in a random manner were carried out to decrease the probability of unexpected variation. Method 4. Determination of phosphorylation degree of egg white powder. The total degree of phosphorylation of egg white powder was measured as previously reported. The powder ingredient will digest in the ratio of 10:1 of nitric acid, sulfuric acid, and perchloric acid, while the digestive fluid becomes clear and transparent. The amount of phosphor in the digest was regarded as the total phosphor of the protein. For the determination of inorganic phosphor, or P, 5 ml of 10 mg per milliliter sample solution was added with the same volume of 15% trichloroacetic acid and then centrifugate and at 300 grams for 20 minutes. The amount of phosphor bound to protein was evaluated as the difference between the total phosphor and the P content. Third 4. Determination of solubility of egg white powder. A portion of 2 grams of egg white powder was dissolved in the 30 ml water in the centrifuge tube, and then the tube was checked for 3 minutes by a vortex oscillator and placed into centrifuge at 6,000 grams for 10 minutes at 4 degrees Celsius. When the centrifugation finished, the supernatant in the tube was removed and the precipitation will be dried to constant white at 105 in the oven. Method 6. Determination of foaming ability and foaming stability of egg white powder. The foaming properties of egg white powder were determined by following the method of Zhang et al. 2019 with slight modification. First, the 15 ml of 10 mg or milliliter egg white powder solution was poured in the cylinder and then homogenized at a speed of 100 R or minutes at room temperature for 1 minute. After 13 seconds, the volume of vivid sample were recorded. Result and discussion. The experimental values of response variable for Volkswagen are presented in the table 1. The model was calculated using the least square technique, and the results were considered statistically significant at p less than 0.05. The coefficient of variable of the model and R rank 2 of statistical parameter for Y1, Y2, Y3, and Y4 are shown in table 2. The adjusted R rank 2 were 0.9362 and 0.8563 and 0.8674 and 0.8919, which suggests that the predictive equation fitted well. Degree of phosphorylation. Regarding the degree of phosphorylation result as present in table 2 and figure 1. Strong linear effect P less than 0.01 of the concentration of sodium triphosphate and quadratic effect P less than 0.01 of the concentration of sodium triphosphate and microwave powder contributes to the degree phosphorylation. In addition, the interaction of microwave power and microwave time had a significant influence P less than 0.01 on the degree of phosphorylation. The response surface plot of the degree of phosphorylation were illustrated in figure 1. The maximum point 3.45 mg per gram was obtained at value 36.23. The concentration of sodium triphosphate 300 microwave power and 90 microwave time. From the response surface 3D figure 1A and B at a certain power 400 weight or a certain reaction time 90 seconds as the concentration of sodium triphosphate increased from 20 to 40 grams per liter. The degree of phosphorylation of egg white protein first increase and then decrease. The improvement at first might be attributed to the collision between the side chain bound to egg white protein and phosphate group of free sodium triphosphate. However, as the amount of phosphate group increases further, electrostatic repulsion might occur between phosphorylated protein and excess phosphate group, while resulting in the reduction of the degree of phosphorylation of egg white powder. In addition, when the microwave time varied from 90 to 150 seconds, the condition of microwave power of 500 watt level provide the most enhancement of the degree of phosphorylation. The data might suggest that moderate microwave assistance could promote the progress of the phosphorylation reaction. Solubility. The solubility of egg white powder under different concentration of sodium triphosphate. Microwave power and microwave time is shown in Table 2 and supplementary figure 2. The regression convention indicates the linear effect of the concentration of sodium triphosphate P less than 0.01, microwave power P less than 0.01, and microwave time P less than 0.05, and quadratic effect P less than 0.01 of concentration of sodium triphosphate. The effect of the mononomial on the solubility of egg white powder was x3 P less than x1 less than x2. In this model, the relationship between solubility and experimental factor was not linear, and the quadratic term and the interaction had a great influence. The interaction between the concentration of sodium triphosphate and microwave power or microwave time P less than 0.01 contribute to the solubility of egg white powder. The response surface plot of solubility of egg white powder were illustrated in supplementary figure 2. The regression convention indicates the optimal condition of the concentration of sodium triphosphate of 22.28%, microwave power of 300 watt, and microwave time of 149 seconds.
Foaming ability. Foaming ability of egg white powder under different conditions is shown in the Table 2 and supplementary figure S2. The regression coefficient indicated the linear effect and quadratic effect of the concentration of sodium triphosphate and microwave power. The interaction between microwave time and the concentration of sodium triphosphate or microwave power contributes to the foaming ability of egg white powder and the solubility of egg white powder. The optimal condition for phosphorylation modification of egg white suggests be the model to enhance the foaming ability were as follows. The concentration of sodium triphosphate 32.5 and 5 grams per liter, microwave power for 415.95, and microwave time 90 seconds. This reaction condition determined by the LSM model predicted maximum response of the dependent variable. After model analysis, the optimal reaction condition for foaming ability were obtained and experiments were carried out under this condition. The foaming ability of egg white powder reached 139.21%, which had 63.91% improvement compared with native egg white, with 84.93%. Next, foaming stability. The foaming stability of egg white powder under different conditions is shown in Table 2 and Figure S3. The regression coefficient indicated the linear effect P 0.01 of three-factor and quadratic effect of the concentration of sodium tripolyphosphate. In this model, the interaction between microwave power and microwave time, or the concentration of sodium tripolyphosphate, contributed to the forming stability of egg white powder. The maximum point 3.45 mg per gram was obtained at value of 35.48 gram per liter and 300 watt and 150 seconds. Fixed at the concentration of sodium tripolyphosphate, and the concentration of sodium tripolyphosphate 20 gram per liter when the power was from 300 to 500 watt. The forming stability first rose and then decreased. However, the forming ability increased continuously in the same condition. It was analyzed by the data that the group of maximum forming ability did not have maximum forming stability. The result might be attributed to excessive microwave power. The one at 218 found that excessive oxidation could cause an increase in forming ability of egg white protein, while a decrease in forming stability. In the Table 3 shown the particular result of measuring value for the degree phosphorylation, solubility, forming ability, forming stability, function properties, and forming properties. The practical result of functional properties and forming properties were 2.32 mg per gram and 90.00 gram per 100 gram and 138.13% and 69.77% and 2.81 mg per gram and 88.19 gram per 100 gram and 137.11%, 69.31% for Y1, Y2, Y3, and Y4. Under optimal condition, the result indicated that the optimal condition for prediction were suitable for microwave assisted phosphorylation of egg white protein. The next, optimization of phosphorylation modification with microwave assisted condition. The optimal modification condition for egg white were achieved using the desirability function method and determined to obtain maximum degree of phosphorylation, solubility, forming ability, and forming stability. The study was designed to obtain the best functional property of solubility, forming power, and forming stability, and correspondent with the condition of the concentration of sodium tripolyphosphate, microwave power, and microwave time. In addition, the model can be a tool for analyzing the forming properties of the model analysis. We conducted a verification experiment. Conclusion: in this work, RSM was established to determine the optimum microwave assist phosphorylation modification condition, the concentration of sodium tripolyphosphate, microwave power, and microwave time. Optimal condition for maximum functional properties, solubility, forming ability, and forming stability, and maximum forming properties, forming ability, and forming stability of phosphorylated egg white protein were obtained. We found two solutions: the concentration of sodium tripolyphosphate of 33.84 gram per liter, microwave power of 419.38 watt, and microwave time 90 seconds for maximum functional properties, and the concentration of sodium tripolyphosphate of 32.97 grams per liter, microwave power of 429.29 watt, and microwave time of 90 seconds for maximum foaming properties, respectively. Therefore, we successfully phosphorylated the egg white protein under this condition and confirmed various pleasurable properties of egg white protein phosphorylation modification. That's all our presentation. About using microwave assisted phosphorylation to improve foaming and solubility of egg white by response surface methodology. Thank you very much for your nice attention, and comment and question are welcome. Thank you.